In this lesson, we're going to take a look at using Kirchhoff's rules to solve circuits. So before, we were able to say, okay, we can take a parallel piece of a circuit and we'll find its equivalent resistance, and then we'll put that with this other piece and whatever, and we were able to get a total equivalent resistance and then work our way backwards from that using current and voltage and what we know about those to figure out the current and voltage through each circuit component. But Kirchhoff's rules allows us to do that without breaking the circuit down into all of its possible little pieces and finding equivalent resistances. Instead, we just use Kirchhoff's two rules, which are conservation of energy and conservation of charge. The first rule is the conservation of energy, which basically says whatever energy we put into it has to be the energy that comes out of it. So if I have a circuit that has a battery, current leaves the battery, goes into the resistor, goes into, say, a light bulb, comes and runs a little motor or something, I don't know, and then comes back to the battery. The battery is producing energy. That energy is being consumed by these things, so that energy is energy per charge, that's a voltage. We'll say this is a positive voltage. These ones are reducing that potential energy and changing it into some other form of energy, heat, light, motion, right? And so since energy is not created or destroyed, the energy in has to equal the energy out, or the sum of the voltage potential differences is zero around any loop. The other thing is conservation of charge. Whatever charge comes out of the battery is contained in the circuit. Now, if it can split and go into multiple branches, that's fine, but the overall amount of charge can't change. So if I have I1 here, then this has to have I2 and this has to have I3. And so we're going to apply these rules to solve circuits. Now, these rules at first might be complicated, but they're not too bad. So let's get a circuit going on that has a battery. Now remember, the long side of a battery is the positive side, and I'm going to put a couple batteries in here. There's one loop, and then I'm going to put another battery over here, and we're going to put in another resistor here and another resistor here. I'm going to call this R1, R2, R3, R4, and we'll have voltage source 2 and voltage source 1. And the rules on this are pretty simple. Choose a direction for current in each branch and indicate the direction using a fat arrow. So the fat arrow is something like this. So this is a branch because it runs from this junction around to this junction. I'm going to call this I1. And then I have another branch that goes between these two junctions, and I'm going to assume that this current goes this way, and I'm going to call this current I2. And then this is another branch that runs from this junction to this junction, and I'm going to say this current runs this way. There's a horrible arrow. I'm going to call this I3. Okay, so I've done that. Now it says for each resistor, place a small plus sign on the end that the appropriate assumed current enters the resistor. So I assumed these currents go this direction. If they don't go this direction, that's fine. They'll end up negative, and we know they actually go the other way. So in this loop on the left, from this junction to this junction, I have I1 going this way. So that means I1 enters here and exits here. And in this branch, I have I2 coming in here, so it enters here and exits here. So I put the plus on the side that it enters. And over here in this one, I have it entering here, exiting here, and I3 continues around, enters here, exits here. So I've done that. Then it says choose one less loop than the number of currents. So I have 3 currents, so I need 2 loops. And it actually says in this case 2 loops. All right, cool. And I'm going to have starting points. So I'm going to have my starting point for this loop here, and I'm going to use the left loop. So I'm going to go around the left loop this way, clockwise. And I'm going to write an equation. So starting here, I don't see anything, don't see anything, don't see anything. And the first thing I see is here, I2. And I2 is going through R2. So it has a potential difference of I2, R2. Now, is that a positive potential or a negative potential? Well, the rule is if I go from plus to minus, then it's negative. So I'm going to put a negative up there. And then I keep going around this loop, and I see I'm back into I1 because this loop is the I1 loop, and it's going from plus to minus as well. So minus I1, R1. And then I see this potential from this battery over here, which is just V1, and I'm going from negative to positive. Remember, the long side is positive, so that's plus V1. This has to equal 0. Now I'm going to choose the right-hand loop, and I'm going to use a starting point right here. And so the first thing I see is V2, but I go from plus to minus. So I'm going to have negative V2, and then plus, and now I'm in I3 going from plus to minus, so plus negative I3, that's going through R4. And then I keep going around, and this is I3 plus to minus, so minus I3 R3. Now, I'm assuming we would know our resistors, but I don't have values in for this. And then I keep going around my loop till I get back to where I started. And now you can see I'm actually going from minus to plus. So I'm going to use plus I2 R2. This has completed my loop, so that has to sum to 0. I'm back to where I started. And I only need one more equation, and I'm going to use a junction equation right there. I'm going to say I1 is equal to I2 plus I3. Now, the thing I want to do is actually solve these three equations. And so I'm going to go to the next page and rewrite these, and I will show you what I mean when I say solve these equations. So here's my circuit and all my equations. Now, these are linear equations, which means we can solve them by elimination, but that's a lot of work. So let me rewrite these so that I have I1 plus I2 plus I3 equals some constant V, right? And so these are not going to be I1, I2, I3. They're going to be R1, I1, R whatever, right? So this first equation, I see negative I2, R2, negative I1, R1. So I'm going to write, and let's just go ahead and give our values. Let's say R1 is 10 volts, or sorry, 10 ohms. R2 is 20 ohms because I'm super creative. R3 is 30 ohms, and R4 is 40 ohms, and then we'll let V1 be 100 volts and V2 be 150 volts. Why not? And so I want my equations all to follow this, like if this was XYZ, right, we would line them all up XYZ equals constant. Well, this time I'm going to line them up I1, I2, I3 equals voltage. So in my first equation up here, I see an I1, so I'm going to go negative, and it's I1, R1, so negative 10 I1. And then plus, my next one, I do see an I2, so I2 says negative I2, R2, so plus negative 20 I2. I do not have an I3 in that one, so I'm going to put plus 0 I3 equals, now I have plus V1 equals 0. If I subtract that to the other side, I'm going to have negative V1, and that would be minus 100 because V1 is 100 volts. And then same thing for my next equation. I see negative V2 is the first thing. I'm going to add that over to the 0, and so this is going to equal positive V2, which is 150. Do I see any I1s in here? I do not see any I1s, so I'll have 0 I1. And then I have plus, do I have I2s in this equation? I have an I2, R2, that's it. So I just need to go, and it is positive, so 20 I2, so plus 20 I2. And then I have I3s. I have two I3s. I have I3R4 and I3R3, and both of those are negative. So I have minus 30 I3 minus 40 I3, which is minus 70 I3. And so I have this equation, I1 plus I2 plus I3 equals a constant. I have this equation, I1 plus I2 plus I3 equals a constant. Now we need as many equations as we have unknowns. We actually have one more equation. We have I1 equals I2 plus I3. Or that's I1 minus or plus a negative I2 plus a negative I3 equals 0. Now the reason I did this is because our calculators, our Texas Instruments graphing calculators, have a function that will actually do all of the elimination for us. So this is essentially a number matrix. I'm going to use the coefficients. So I have 10, negative 20, 0, negative 100. And then I have 0, positive 20, negative 70, and 150. I'm pulling just the coefficients. And I have 1, negative 1, negative 1. This is plus a negative I3, and a 0. All right, so those are the coefficients on my terms. You'll notice this is a matrix that is 3 high and 4 wide. And we're allowed to do lots of things to equations so that we can get things to eliminate, right? We can multiply them, we can add them, we can subtract them. And so all of those rules would allow us to get equations that would get ones in each one of these places. This is what's called putting a matrix in reduced row echelon form. I'm not going to go through all the mathematics on that, but I am going to show you how your calculator can solve this in a hurry. So I've pulled up my calculator here, and you can see right above the inverse button is this matrix button. So I'm going to go second matrix, and I'm going to go edit. So I arrowed over to edit, and matrix A is fine. And it asks for how high do I want this? Well, I have 3 rows, so it's rows, 3 rows. By 5, 1, 2, 3, 4 columns, because I have the variables and the constant. So it's a 3 by 4 matrix, and I can push enter. And then I just have to type in my coefficients. So that's 10, negative 20, negative 20, 0, and negative 100. Make sure you use the negative sign, not the subtract sign. And then I have 0, 20, negative 70, and 150. And then my last equation is simple. It's 1, negative 1, negative 1, and 0. Enter. So I have my matrix that has just the coefficients from my linear equations that I wrote. Now I'm going to push second quit. I'm going to go second matrix again, and I'm going to arrow over to math. And there's a whole bunch of things here. You can get a determinant, you can do an identity matrix, you can do an augmented matrix, you can put a matrix into a list. But what I want is this one. This is RREF. That's reduced row echelon form. And I'm going to push enter, and then I have to tell it what I want it to reduce row echelon form. So again, I go second matrix, and we put our matrix in matrix A. So I pick that one, close my parenthesis, push enter. And here's what it did for me. It said, oh, I'm going to go ahead and solve my systems of linear equations, so I have 1s and 0s. So what this equation basically reduced to is 1I1 equals 12. Cool, now I know I1. I1 is 12. This one, since this is in the I2 spot, shows me that I1, I2 is equal 11. Cool, now I know I2. I2 is 11. And this one tells me that I3 is equal to 1. So I know the current in each branch. I know I1, I know I2, I know I3. So I can actually use my calculator, and I have my final answers. I1 equals 12, I2 equals 11, and I3 equals 3. And once I know the current through each resistor, then all I have to do is multiply by the resistance to get its voltage drop. So that reduced row echelon function on your calculator is handy. It'll work for any system of linear equations. If you have one more unknown circuit, unknown current, then you're going to have one more equation. So you would extend your columns to 5 and your rows to 4.